Automatically landing a rocket stage. How hard could that be? SpaceX has shown us the way, and we've seen multiple landings of first rocket stages in real life. And I was thinking, if I can launch a rocket in Kerbal Space Program with Python 3 to be exact, how hard could it be to program this? I've used kRPC, the plugin, and I used kRPC 0.3.9. 0.4 is just out. I was just too quick with finishing this. And when you want to use this in Python, of course, you have to install a library. It's called the kRPC library. And also you need to run a server, but I'll show you in a moment how that works. So let's have a look at the code. And the first thing, what happens when you are trying to discuss your own code you've just written, the more you discuss it, the more stupid things you start to find. Of course, first of all, the not stupid thing is that I start with importing the kRPC library because I have to use it. But then I found out I've imported time twice and I've imported logging while I didn't use it. So the newer version of this script, which is available in GitHub, has this changed. Then when that's done, we have to make a connection to the kRPC server because that's how kRPC works. So you're starting the kRPC server from Kerbal Space Program. It has a window that looks like that. When you make a connection with your Python program, you can see actually what is running on it. You see here that I have my automatic landing of first stage script running there from localhost, so that works. And let's program some stuff. So I started this program with three functions actually. Two functions to write stuff to screen, so I can follow what's happening with the rocket, and it's also a good indicator when I'm looking at the KSPC screen if something is going wrong, because then the panel disappears. Anyway, I've created a function to prepare the screen message. It has some settings that I only have to run once. I've used these settings before. The panel is a little bit bigger than I've used in my previous Python with KSP script. What has changed is the text size. It's smaller, so it won't be that readable when you watch this video on the tablet, unfortunately. But when I used the previous text size 16, stuff would fall off halfway from the panel. I don't know why, but now I get to see everything that I want. So that's that. And to use this, I've created another function. It's called the write screen message. And that is the one that I've used heavily throughout in the code to write stuff to screen. And the third function I've created is the interval print, because I need to write some stuff to the command prompt, at least to the output there. And at first I wrote the altitude and speed every time in the while loop, and that happened too fast, so I created an interval in it. Okay, now to the real flying part. So first of all, there's a target apoapsis of 75,000 meters. We're doing a real launch. We're going through the motions. We're not actually going to launch something in orbit, but we're going actually to launch this rocket, and it will actually have a trajectory with an apoapsis of 75,000 meters. Also, we have an island heading. This is the heading where I want to launch the rocket. And I haven't done it in this version yet, but in some future version, I want to land it on the island near the coast of near the KSP with the landing strip. That's where I want my rocket to land. But I don't have the correct program now to do that yet. For now, we just we splash down this rocket safely in the water. That's all I want. You have to go to through this step by step. Then we have an ascent trajectory. So basically, instead of one hard gravity turn, I've done the turning in steps, and I created a Ascent Trajectory dictionary. It's a dictionary object in Python. Dictionaries are key value pairs, and in this case, I thought it would be handy to have a key with just a step number and a value. The value in this case is a list of 4 parameters, and the first parameter is the altitude at until which things have to change, then the pitch, then the heading, which is just the island heading, and then the percentage of thrust. So what is happening when we're going through this dictionary with a for loop? So first we launch straight up until 1000 meters with a thrust of 100%, and then we, for example, a little while further until 9000 meters, we pitch 75 degrees and thrust 85%, just to make sure we're not hitting the terminal velocities. And then somewhere at until 33,000 meters, we're pitching 45 degrees and 50%. So that's basically how it works. It's a little list of things to work out to do this trajectory. Then we have to do a little bit of initializing of stuff in kRPC. We need to have a space center that we call KSC. We have a vessel that I've called Rocket. And I also saved the rocket name, which is useful later on, but I will show you later when that is the case. We have an orbit body reference frame because we try to get in orbit at first. Then we start the engine, but that doesn't mean the rocket leaves yet, because the rocket is held down with rocket clamps. So this is just starting the engine. It will throttle 100% for 1 second, that is the sleep, and then we actually are going to lift off. So here we go. So we see countdown, and then 1 second, and there we see it doesn't always go straight up. It sometimes gets a little push by the clamps. It doesn't always go well. Sometimes it even veers off back to the ground when it's pushed against it too hard. But here we see it go well. So that was liftoff, and now we go through all the parameters, through the dictionary, the Ascent Trajectory dictionary. So first we print it. This is just going to the command line, and then until the first parameter, that is the altitude. So until, for example, 9000 meters, we go with a pitch parameter 1 of 75 degrees and a heading of 117, or the island heading, and we throttle and with a percentage, I think it was 70% or something, and we show that on screen also, which could be handy. There we go. So there we see the rocket make go to a new step above 13,000 meters, if I'm not mistaken. So that works pretty well. And when I find out that this trajectory is actually not that good, I can change that later on, make it launch steep, make the launch trajectory steeper or anything. All that is possible. But I don't have to go through all kinds of programming lines, computer code to change that. It's just a data set, basically. And then we go, I think, to the next step, because after 33,000 meters, we are on a new plan, and that is something I should see the code just in a second. Because then we are just going burning until the apoapsis. That is the code. That's the code here. So we're going to keep burning until we have a trajectory that will have an apoapsis of 75,000 meters. and we keep pitching 45 degrees and heading one in the island heading. And when that is done, we stop the engine, and basically normally you would just remove the we decouple the second stage. In this case, we have some other plans, as you soon will see. There we of course, first of all, we have the payload fairing and the decoupling, and then it's time for the second stage. Now, the funny thing about this version and this vessel is that it actually it's controlled from the first stage, and there are good reasons for it. But now we have to switch to the second stage. So what you do in Kerbal in kRPC, you ask for a list of all the vessels, and you find your own vessel and the vessel you want, and pick that one and make that the active vessel. Now in this case, the funny thing is, when you ask for that list, you not only get to see your own rocket parts, but you also see everything else in space. For example, the large MF space station is also there, which has nothing to do with this whole exercise. But what we're going to use is the relay part, because our second stage is actually not just a satellite, but also a rocket part. It has a fuel tank, and it has a rocket engine, but it also has a relay dish. So we have to find the part that has the name of the rocket with relay at the end of it. So this is how we find that, and when we find that, we make that the active vessel, and we also make an object or a variable called second stage, and this is what we use to command it. And here we get to a very, very interesting part of maneuvering a vessel after switching to from another vessel. So we're pitching with before this switch, we were pitching 45 degrees and heading 170 degrees. But after the switch, has been a reset, and it took me quite a while to find that out. So what's happening is I was flying this satellite with its rocket engine in the direction of 45 degrees, and now suddenly the pitch is 0%, and also the heading is 0%. Before I found that out, I had very, very strange results, but now I understand, and I can adapt to that situation. So the second stage heading, that little variable there, that is now 0, because I'm actually heading not 170 degrees, but actually to 0 degrees, and I'm pitching 15 degrees, and that's actually a bit too high. That was, but okay, I can change that later on. And the first stage, when switching back to the first stage, same thing. Yeah. So again, we ask for a list of all the vessels, which is really great. That you just get a list of all that. And by the way, I could have switched to the space station if I wanted, but of course I don't want to. I want to switch to Falcon 5A, which is the name of my whole rocket and spaceship. And but first thing when I switch is I have to throttle down to 0% immediately, because if you we're throttling the second stage and kept it like that, and you switch back, the program thinks you're still supposed to throttle, so you need to turn that off immediately. Here you see that. And then I turn the RCS on. You could shortly see that also. And that helps me to turn the rocket around, because I want to make a reentry burn. I have to make a reentry burn basically parallel to the surface of the planet. And the thing is, here also, the rocket is now pitching 0 degrees. So when I want to go back parallel to the well, like that, I need to turn it back 135 degrees. Only then I can make a safe burn, a re-entry burn. So first I give it 20 seconds to turn around. You see the 4i is range 20. That's just to give also have a possibility to see a countdown. Then we give it a slight throttle. The gimbal of the rockets will allow it to turn a little bit faster, and then we burn, but 100%. But of course, we want that to happen as soon as possible in the right direction. So that's why I gave it all the time to make that turn first. So there we go. You see the RCS worked, and we are turning, and we see a countdown happening in the lower left in the panel. We're not turned quite yet, but we now have the throttle of 5%, and then after 2 seconds or so, we're really burning hard, and this is the actual re-entry turn. Oh, I'm so glad to see this working now. This was it was such a headache because I didn't understand that pitch and heading thing. And now it's time to re-entry, so we throttle back to 0, and now a whole lot of nothing happens actually until 20 kilometers altitude, and that is where we deploy the air brakes. This is also interesting. You can't directly direct the air brakes from kRPC, but you can direct an air action group, and you can add the air brakes to that action group. So you need to create your craft. By the way, I have my craft downloadable from GitHub. And you need to say that is action group 1, and then you can run it. You can just tell it to deploy to toggle from kRPC, and that is what really works. That really works great. And then we also have a stupid little command to tell the rocket to run retrograde, but that actually doesn't. I don't think that works. I turn the rocket retrograde. There you have the rectangle. I asked it to turn retrograde in 2 different ways, and this I don't think this really worked, but I have another way, and that's very essential to really burn retrograde when you are landing. So I'm glad it actually worked. So here we have the deployment of the first of all, we're going in the re-entry rather fast. This is a good time to time warp. You can do that during your program, by the way. And when we reach the 20 kilometers altitude, we deploy the air brakes. And there's that moment. So you see it braking rather fast. It really works. So the air brake really helps. And it looks a bit like a real Falcon 9 rocket. Now, a whole lot of nothing again happens until 2 kilometers altitude. And there we do something really strange. Because I haven't actually calculated all the physics parameters for the good burn. Instead, I have created a little calculation on the back of the envelope, and it's called the Crude suicide burn factor. So what's happening? So at an altitude of 2 kilometers, we measure the speed, and so here's the altitude, and we measure the speed, and we just multiply it by a Crude factor, and that is the altitude at which I'm going to start burning really, really, really hard. And I've tried this scenario several times, and it actually works rather well with this rocket. I wouldn't say it would work with other rockets. When you would really do this the best way, you would calculate the ISP of the rocket engines and the amount of rocket engines, and calculate how much acceleration these give. But okay, I haven't done that yet. What we do is, at the moment that we reach the Crude suicide burn height, we start to go really retrograde. I think this is actually working much better to go retrograde. So that the retrograde is in the you see the target direction 0, -1, 0. That is the actual retrograde command, and then we start the real suicide burn. This happens after the Crude suicide burn altitude is reached. We keep doing this whole thing until the altitude is 1 meter. Might be a little bit too low because the rocket is it should go something like the halfway. But when the speed is higher than 50 meters per second, we throttle 100%. There's another mean altitude factor there, just to make sure that when it burns too hard, it doesn't go up too soon, but okay. And then when the speed is between 50 and 20 meters per second, it throttles 50%. And when we're above 8 meters per second, we start throttling only 26%. This is a good speed that slowly brings the rocket down. This doesn't brake too hard, doesn't brake too soft. Basically works. And we try to turn off the retrograde here, but it actually doesn't work. Why do I turn off the retrograde? It's because the retrograde, when your rocket is very close to the surface, when your speed is very low, it might go all the way until it's up. So that's not so good. And now there's a stupid mistake here in my code, which I shall change. And when the speed is below 10, it will deploy the landing gear. That actually is not bad, but it also throttles to 0. So we have a situation between 8 and 10 meters per second where the computer has to decide whether it shall throttle 26% or 0%. So that's my mistake, and that's something I have to change. But these are the things that you notice when you try to explain people what your code does. So it's actually not bad. It's not bad to explain things to people. You learn more and you get better code, I hope. So there's that, and let's see how it works in the real world. And that is how you land a rocket stage. I hope you enjoyed it. I'll keep improving my code and come back when I actually manage to launch a rocket stage on land on exactly the right spot where I want it. But that is for some other time. Thank you for watching and see you next time.